Okay, so let's start. Hello, everyone. Welcome to this week's Scrum seminar. And we have two talks today. And okay, because of the some issues, like we go with the second talk first, and then we'll see if our first speaker is going to join us. And since Yuhan is not here because of some personal issue, Yuhan, could you do a short, brief introduction of yourself? Because I don't have any information. Sorry about that.
Yes, so this is joint work with Yuhan and also Tang. So I think you guys mostly already know Yuhan and also Tang. So I'm gonna do a little bit of self-introduction. My name is Yuan Andrew. You may call me Yuan for short. I am Daniela Venturi professor, first PhD student at University of California, Santa Cruz. So I spent then, after my PhD, I spent 2 years at the UC Merced, actually worked with Tang. Now I'm a postdoc at the Lawrence Berkeley National Lab, working aside a different problem. Yeah, so that's about me. Nice to see you, everybody.
Nice to see you. So you may want to share screen and start your talk.
Yes.
Are you able to do that?
Let me see.
Oh, let's see.
You see the slides?
Yes.
Okay, so let me put it in the slideshow mode.
Great.
Yeah, everybody?
Yeah.
Okay, start right now?
Sure.
Oh, yes. Thank you, everybody, for coming to my talk, our talk. So today we are going to talk about how to learn stochastic dynamics with a new neural network architecture that we invented. It's called Statistical Informed Neural Network. This is joint work with Yuhan and also Tang. We published a paper in arXiv and we posted the link here. So this is the ID. So this is a title for our talk and also the title for the paper that we submitted. Okay, so let's first talk a little bit about the motivation of our research, and it's mainly about the stochastic reduced order modeling. Right now, we in modern computational science, especially in computational mathematics, we are always facing the problem of the curse of dimensionality. That is to see that it is often the case we need to solve a very high dimensional dynamic system. And in order to resolve the full dynamics in a long time scale is often infeasible because of the dimensional problem is too high. However, it is also often the case that for these high dimensional systems, there's only some local information or local observables that really of scientific research interest. So let me give several examples here. So first of all, is an example from the fluid mechanics. So in order to resolve the fluid mechanics, especially for the Reynolds numbers is very high, you need to solve a 3D Navier-Stokes equation, and it's very expensive. However, if we want to know what is the transport property of the fluid, we can choose several representative characteristic Lagrangian particles immersed in the fluid and what is movement. So if we can get some reduced order model for this movement of these particles, then we can understand how the turbulent really transport particles. Another examples come from the MD. Suppose we wanted to study the dynamics of proteins. So which consists of large amounts of atoms interacting with each other. So what we can do is to reduce computational costs, we can develop some so-called cost-grind models, and which basically you divided these atom chains in different kind of large functional groups and to see how they interact with each other, and eventually to help us to gain some understanding of some important physics like protein folding. Also, an example from the molecular dynamics is the enzyme dynamics. Enzymes basically large proteins. But we now already from the understanding of chemistry, that is not all these atoms in this large protein really participate in the chemical reaction, but only a very small portion of it, which is known as active side. So this is the side that different molecules binds here, and also and the proteins participated in the chemical reaction and so all these three examples just tells you that for large dimensional systems, it's often the case that some low dimensional observables is something what we are really interested in. So we wanted to get some model for that. So this type of model is called reduced order modeling. And also like the MD cases, we often need to deal with some very small, small scale behaviors, dynamics. So you have to consider for most of the cases thermodynamics, therefore the randomness start to kick in. So this problem will be stochastically reduced auto modeling. So our proposal is to use neural network to learn the stochastic dynamics. So right now, it is fair to say that we have seen a revolution, first starting from the computer science, and now is becoming widely popular in the whole scientific areas in physics, chemistry, that it apply the modern machine learning architecture to do scientific problems. I think the first groundbreaking work, and especially from the computational mathematics side, is actually George's group's physics-informed neural network. So I'm definitely not an expert in this field, and we have so many experts here. And so I only just share my own personal understanding of this framework, and please correct me if I'm wrong. And also allow me to violate the copyright here and use some of the figures in your paper. All right, so basically physical neural network, as I understand it, is used to create some numerical solver for some dynamic systems, especially for some partial differential equations. So for this case, we know what the governing equation of some physical process really is. For instance, the fluid, we know that it's governed by Navier-Stokes equation. So we wanted to train some neural network and to use it to solve this type of equation. So the basic modeling module of physical informed neural network is a multi-layer perceptron structure. So specifically, if we wanted to approximate the solution to a PDE, let's say UXT, this represents a solution of a Navier-Stokes equation. We form a neural network, which is multi-layer perceptrons. And this neural network takes two input, which is the space-time location, X and T, for this PDE. And then this input were injected into layers of neurons connected to each other. And it just spills out the solution to the PDE, that is UXT, the function. So if we only have this part of the model, then it will become a somehow like a black box model, and we don't know what happened really here. So the real meaningful part and a really creative part of the physical informed neural network is combine the second part of the loss, which is since you already the output of the neural network is the solution to some PDE, and you know that is the governing law for this PDE. So we can take different derivatives, time derivatives, spatial derivatives, and also compare the derivatives of the output of the neural network with the result of the PDE. So the laws of the physically informed neural network are combined two parts. The first part is that you compare the output of the neural network with the solutions that you know. And also the second part is you take the derivatives of this neural network, that is UXT, and compare it with the governing law to calculate another loss. So you compare, you add up these two mean least squares, for instance, together, and then you just update, you just minimize this loss function, and also with these to update the parameters in your neural network. So this is the idea of neural network, and it has shown to be very successful solver for lots of ODEs, for a lot of ODEs and PDEs. Here I just present an example that I copied from the numerical simulation result from George's group. So this I think is a typical example for flow passing from a cylinder, and you want to study the heat transport associated with this process. Here just the right hand side will show the theta is the temperature field, U and V is a velocity field, and also the P is a pressure field. And this is the simulation result of physical informed neural network and the associated error. So this is the physics. This is called a learning solver strategy. So basically, we use neural network to develop solvers for dynamic system. Neural network can also be used as some learners. So what it mean here is we don't know, for instance, the governing law of some physical process really is, and we wanted to recover it from the observation data, no matter it's numerically or it's experimentally. And this is basically is also called a inverse problem in many fields of mathematics. So a typical example that a neural network developed in this regard is called a neural ODE. So we know that if we know some dynamic process and we know that there's no randomness here, so we can assume that it is governed by some hidden ODE we don't know yet. So we can propose that it is given by this dz by dt, and it's given by the right-hand side some f function with some parameters. So we don't know this f function really is. And we also know that it is a deterministic system as long as you know the initial condition of this dynamic system and also the derivative, i.e. this f function, you can know the dynamics, you can determine the dynamics. So the idea of a neural ODE actually is we just use two neural networks. One is actually a recurrent neural network, in short RNN. Another one is a multi-layer perceptron. So you use the first part, the RNN part, to learn the initial condition of this dynamic system. And also this multi-layer perceptron is used to model the derivative, i.e. this f function. So if you know this two part, then you uniquely determine the dynamics. You know the initial condition, you know the derivatives. So in order to train a neural network, what you do is you collect some data, and this data was used using as input of the RNN, and then the RNN will spit out the initial condition of your dynamic system. Then you plug this initial condition to any ODE solver for the MLP modeled derivatives, and then you collect the trajectories, you compare the trajectories with your data, and then you calculate the loss, and then with the loss, you update the parameters in the RNN part and also the multi-layer perceptron part. So basically, with these two parts, you can learn hidden dynamics, which basically given by the initial condition and also the derivatives. So we can know that this is a typical inverse problem because we don't know the underlying equation. And in the ODE, the equation we still use it, and it was used in the modeling part. So the right-hand side, I just shown an example copied from their paper. And basically they use these neural ODE to recover hidden spiral-like dynamics here. So we can see that you have some ground truths, and you can use neural network to learn the hidden dynamics to make some correct prediction. And because you can learn the dynamics, which is given by this ODE, you can also do dynamics extrapolation, which basically you extrapolate it in time and to see that it will whether make correct predictions in the future. So this is also the simulation result they obtained. So this is the typical example of neural network used as a learner and also as a solver. All right, so around 3 years ago, people started to think about considering how to use neural network to model stochastic dynamics, especially stochastic differential equations. So the major breakthrough is called a neural SDE or the jump SDE. So the idea is actually pretty similar to the previous neural ODE example. So suppose we know some stochastic dynamic. We know that the dynamic is stochastic. And then we assume that it is described by some stochastic differential equation given by this form here. So dz equals fdt plus omega dwt, where this dwt, depending on the situation, for most cases, it can be Gaussian white noise, and it also can be other stochastic forces like, some, for instance, Levy-Fly, some other stochastic processes. So we wanted to basically use these, answers, and then to use neural networks to represent the two part with the unknown part of this stochastic differential equation, i.e., this f, these derivatives, and also the the omega function. So with in the neural ODE or jump SDE case, the multi-layer perceptrons are used to model this f function and this omega function. So the idea is pretty similar. You just collect the simulation data from the trajectory, and then you update the parameters, calculate the loss, update the parameters in these multi-layer perceptrons, which models this f and the omega function, and then you get the learned model. However, I have to emphasize that for the stochastic differential equation case, we found out these framework is actually have some major drawbacks. So generally speaking, there are two drawbacks. So the first one is different from the previous ODE case or any kind of deterministic situation. That's because you have a stochastic differential equation, the trajectory that you generated is random. So different kind of realization, numerical simulation with that, you get different kind of trajectories. So that is to say that in order to update the parameters to calculate the loss function, not only you need to store the data for the z, which is the state space variable, you also need to store all the realization of this stochastic, random forces. You sample it. You have to store it in each time. So this will cause you a huge storage burden for the SDE. Otherwise, you cannot do train the parameters in your neural network. So some people probably argue that, even maybe for low dimensional system, the computational cost is not very high. So the second problem, the second limitation for this framework, it makes it worse. And also that is, we think it is probably practically impossible to apply it in reality. That is because in reality, it is impossible for you to get what the stochastic force realization really is. What you can only observe from numerical simulation or from the theoretic measurement of some, random movement of some, dynamic, some particles, is that we only know the stochastic trajectory of Z, which is different for each realizations. We don't know what are the hidden, the random noise term that is really generated. So it is impossible to know that. Since it is impossible to know, so how do you use this current framework to learn, the neural network, the F and an omega function for that? That is impossible. So you can't apply it in reality in any sense. So, so this, I think, is the major drawback of the, this is the major drawback of this current framework. And because essentially I would have mentioned about this one is because what you eventually do is you store the different kind of realization of the random stochastic processes. And then, so what you eventually seek is also a pathwise convergence to the stochastic process as shown at the right-hand side. And we find out, as I will gradually explain, it is not necessary to get a pathwise convergence. Is because in lots of applications, we don't need to exact pathwise convergence to the exact stochastic process. For the most of the cases, as long as we can guarantee that some stochastic characteristics of the stochastic process convergent to the target one, it will be enough for most of the modeling. So this actually motivates our research. So before we present the neural network we developed, let's just do some overview, of what is the traditional way to learn a stochastic dynamics. And this is the example from molecular dynamics. It's called a Causal-Graham generalized Langevin equation. So the physical scenario here is I show at the right-hand side maybe comes from some Causal-Graham problem of some molecules. So suppose we're trying to study, again, the protein dynamics, and we know that proteins consist of chains, amino acids. And for most of the cases, we don't really care about the wiggling of very small portions of this chain of amino acids. Well, what we can do to make our life easier to perform simulations efficiently is to divide this chain into different kind of function groups. And these function groups are known as Causal-Graham particles. So if we can get some effective dynamics for these functional groups, these CG particles, then we can maybe use it to perform longer time simulation and get it eventually develop the model for this reduced, for the CG particles. So the classical way to do it in statistical mechanics involves the usage of the so-called projection operator framework or the Merz-Wanzig framework. Specifically, what you do is you design some projection operator P. So what the function of this projection operator is for any input function H is just projected into the vectors of a finite dimensional space. And this finite dimensional space consists of the momentum and a position of these Causal-Graham particles. So by invoking a very complicated framework called Merz-Wanzig, then eventually you can get some reduced model, a closed equation, at least formally closed equation for the Causal-Graham particles. So the momentum and position of that. So this equation is normally very complicated, so you need to perform several approximations to approximate it. So eventually you will get a form which is called a generalized Langevin equation for the Causal-Graham particles. So as I showed it here. So this equation can be used as an ansatz to model these CG particles. It is ansatz because it is almost impossible for complicated cases. We know that what is the exact form of this K function here and also the fluctuation forces here. So the K function is known as a memory kernel. So as you reduce the dimension of the system, actually the system will have a memory effect. This is the reason why you have a time convolution kernel 0 to t of the K multiplied US here. And also the system is random because you're starting the molecular dynamics and you have to put it in some statistical ensemble. And this is the source of the stochastic forces. So you get an integral differential for stochastic differential equation. So this is the Lagrange equation. So the typical way to learn what the memory kernel and also the fluctuation forces really is, you can use some data-driven method. So for instance, we can assume that this memory kernel is composed of some, time series, some basis functions expansion with some unknown parameter ki. And then you can use the correlation functions of these observables, like the momentum correlation function, for instance, to update this parameter, to update the parameters in the memory kernel. And then once you learn the memory kernel, you can use some physical law. For most of the cases, you use the second fluctuation dissipation theorem, which allows you to perform some modeling for the stochastic forces. Here, just to show you an example, to use the generalized polynomial chaos expansion or the generalized Kaufman-Levy expansion to represent the stochastic forces. And as you can see, that the whole classical way to do the stochastic modeling for this case is actually rather technical. You use a bunch of equations, bunch of the approximations, and also it also have limitations. And this limitation mainly stems from the modeling part of the stochastic forces. For instance, if you use the generalized Kaufman-Levy expansion, it is for stochastic process. It's actually really hard to guarantee that you can get a convergence result that is higher than second order. And this both imposes you theoretical limitation and also numerical simulation, theoretical limitation and also numerical limitations for this type of forces. So, and also the most deadly thing is it is relatively hard, and I think it's generally hard, to generalize this mechanism into high dimensional cases. For instance, what I show, the picture at the right-hand side, if you have very high dimensional system, and also this system is highly heterogeneous in the sense that for different functional group, you need to assign a different memory kernel and also the fluctuation forces, and they're different from each other. And then you basically have a nightmare, okay? So this, the learning of all the parameters in the memory kernel and also the fluctuation forces is extremely expensive computationally. And also you might have other stability problems, for instance. So what we want to do is we wanted to design for machine learning frameworks which keep some good part of the traditional method, which help you to learn some statistical characteristics of the CG particles, for instance. And also you want to avoid the major drawback of the neural SDE model that we just discussed. So in generally speaking, we seek a simple enough, but also flexible machine learning framework that is easy to generalize to higher dimensions. So these lead to the development of the so-called statistically informed neural network. So before we talk about specifically what a neural network is,
Johan, can I ask a question here?
Yeah.
As you're looking ahead, what would you assume that mean square displacement? What kind of data would you have to? What is the data?
For the CGLE?
Yeah, for example.
Oh, yeah, the data that you collected, for instance, you perform the full-scale molecular dynamic simulations. You record the trajectories of these CG particles, and then you can calculate, for instance, the correlation functions for the momentum of some CG particles. And this is the data, for instance, you collected to learn, for instance, the memory kernel.
I see. So you have the fine-grained molecular dynamics, all the trajectories, everything available, but basically you need just a correlation function.
Yes, correlation function. And also in order to learn the stochastic forces, you need to use, for instance, the second fluctuation dissipation theorem, and also to assume that somehow in the statistical dynamic limit, your dynamics will approach to the equilibrium dynamics and satisfying equilibrium distribution, for instance.
Okay. Thank you.
Yes, thank you. All right. So before we present the specific design of statistics informed neural network, since it's built up on recorded neural network, so let's just start with some review of this architecture. And especially I wanted to emphasize is that your recorded neural network can be used as a universal approximator for open dynamic system. Here is the computational architecture for a basic, very simple one-layer recurrent neural network. So the system takes the input, which is a time-dependent vector x. So then you inject this input into the hidden state of the neural network given by described by h. And then for each step, you can apply some matrix to get the output. So this is a very simple structure. So if you wanted to, you can write down the updated rule for this one layer RNN, and it's given by very simple form. So the nested hidden state HT plus 1 is updated by applying some sigmoid activation function into the following equation. So first you need to use a coefficient matrix W to multiply the hidden state of previous hidden state HT, and then you need to combine it with another matrix U, multiply the input of the previous XT, and then you minus some bias vector theta. And then for each step, you generate how to generate the output of the neural network. It's simple. You just design another coefficient matrix V, and you apply it to the hidden state HT. Then you get the output. So you can, a very simple observation. You find out actually this updated rule for the one layer RNN is actually very similar to the updated rule of a discrete open dynamic system given as it is. So the ST is the state vector for the open dynamic system. The dynamics is open because you have an external input, which is XT. The output of this open dynamic system is just a simple function F, which is a function of the observable, is a function of the state space vector ST. So the OT is you can understand it as some observables that we want to model in some dynamic system. And it turns out the coincidence, similarity between the updated rule for RNN and this open dynamic system is not a coincidence. In fact, it was proved by late 90s by Schaffer and Zimmerman that you can use this simple one-layer RNN architecture to universally approximate the discrete open dynamic system. So the Schaffer and Zimmerman's result can be simply stated as follows. So for any sigmoid activation function sigma, if you have a wide enough neural network with basically giving enough hidden state, you can use this one-layer RNN to universally approximate an arbitrary discrete open dynamic system in finite iteration steps. So the existence of universal approximation of the RNN architecture basically tells you the potential of the neural network structures in terms of approximating open dynamics. Open dynamic systems. So although in reality, we almost never use a wide enough neural network to learn something. And also, the universal approximation theory at least tells you the potential of this architecture. So I think this is interesting and also important theoretic foundations for neural networks. So the second thing that we need to consider is how to get some stochastic RNN model, which allow us to simulate some stochastic differential equation. So the core problem here is actually simple. How to change the deterministic RNN structure, which is completely deterministic, and embed the noise or randomness in somehow, and then to use it to approximate stochastic differential equation. Actually, the previously mentioned universal approximation theorem actually give us a good hint what to do. So suppose, let's just say, we wanted to approximate Euler-Maruyama scheme of some ordinary differential equation, of some stochastic differential equation. And this stochastic ODE is given by, for instance, this ethos diffusion. And then we write down the Euler-Maruyama scheme, which is given by the following form. And you can see that if we fix the step size delta t, so for instance, 0.01, and then the updated rule for this SDE in the form of that is exactly the same as the ones for the discrete open dynamic system, as long as you simply just replace the external input xt into the realizations of Gaussian white noise, i.e. this CT. So what we have here is actually we can do a very simple modification to the recurrent neural network to make it stochastic. That is, we just simply replace the input of different realizations of Gaussian white noise and use that as the input of a neural network. Then you naturally get a stochastic variant of it. So the next question is, can we get a similar universal approximation result for the simple one-layer stochastic RNN? And actually, it is the answer is affirmative. So this is a result that we proved in the paper. So it is very similar. So that is, if you're given enough hidden state, i.e. you have a wide enough neural network, so you can use these very simple stochastic RNN to universally approximate any kind of Ito-type differential stochastic differential equations asymptotically almost truly. So we need to, if given time, we need to explain a little bit why we only have asymptotically almost surely guarantee here. But right now I would like to focus mostly on the numerical part. Before we presented the, for the extended, I wanted to comment here. So this structure, you can see that it's very simple. Basically, we didn't do any kind of structural changes to the RNN model. So the good part of this simple architecture is you kept all the parameters in the neural network to be deterministic. Nothing random here. The only randomness that is external, that is external white noise that you injected. So what is the good part of this? Is actually it's very easy to train the neural network. You don't need to do any kind of modifications of any kind of frameworks. For instance, and it also is very easy to implement it in the current platforms like PyTorch or TensorFlow.
I have a question, Jan. So the noise is white noise, or I can dial any color of noise?
I think you can do it colored noise. Also, you can also not only need it to be Gaussian white noise, you can use, for instance, using some Poisson process, and also it works. I think the way to choose noise depends on the thing that you want to model. So this is the point. So for instance, if the stochastic process that you want to use the neural network to model have some compact support in some finite dimensional domain, then I think it is maybe not a good idea using Gaussian white noise. You use a different kind of noise. But if you have no compact support, for instance, then I think the Gaussian white noise is the easiest case to try at least, and because it's actually directly stems from the SDE.
Okay, thank you.
Yeah. So let's just put the insight I just showed into practice. So if you wanted to apply the things I just mentioned in the practice, you also need to solve two problems. The first problem is the one-layer stochastic RNN model I just described is too simple. In practice, almost nobody used a wide enough one-layer RNN to do any kind of learning because it's too expensive in terms of computations. And also, in reduced order modeling, especially stochastic reduced order modeling, like the coarse grinding problem, we see that for most of the cases, the system is not Markovian. It's not governed by some ethos diffusion. Instead, it was the governing equation, like the generalized Langevin equation, is stochastic, and it also have a memory effect, which is make the system non-Markovian. So the current state not only dependent on the previous time steps, but it depends on all your history. So actually, we can do a very simple modifications to the RNN model and actually use a different RNN model, which actually solve these two problems in one shot. That is, we just propose to use the LSTM, which is short term for long short-term memory effect, a memory model, and use these as the basic modeling modules for the statistics for the neural network. What I read, this LSTM is a special type of RNN model. It is definitely more complicated than the previously mentioned recurrent neural network. So the specific updated rule for the neurons is pretty much complicated. So I don't want to spend time on that, but I can give a very intuitive explanation why this can handle the system with memory. If you write down the updated rule in a very abstract form for these LSTM modules, you will find out that the updated rule has an additional term, which is marked here as a red color, CT. This is known as the cell state for the LSTM model. So this cell state is additional part for the updated rule. And this term that modeled all the history information, somehow modeled or stored all the history information for a neural network. And then we can do a very simple stochastic variant of it to simply replace the input of the LSTM modules into, for instance, Gaussian white noise. Then we naturally get a stochastic LSTM, and these will be used as the basic modeling modules for the statistics for the neural network, which I'm going to discuss now. Okay, so this is the basic architecture of the statistics for the neural network, a sign that we invented. I think this model has some simple structure. Excuse me. So the input of the neural network are different realizations of a Gaussian white noise, as I just mentioned. And then these Gaussian white noise are injected as an input for the LSTM layers. And then the output of the first layer LSTM will be injected as an input of the second layer LSTM, so on and so forth. So the last layer of a sign is the MLP layer, which stands for multi-layer perceptron. So the function of this layer is to project or to tune the output of the LSTMs into this target stochastic process with the dimension that we wanted. So what makes the statistics for neural network very different from, for instance, neural SDE is actually the training. The training part is very different because what we do is we just design this, train this neural network in ensembles, and then we take the ensemble average for this target stochastic process is generated in order to calculate the statistics, important statistics of the stochastic process. And that, for instance, the important statistics include, and not only, but include, for instance, the equilibrium statistic probability density of the stochastic process, or the time autocorrelation functions of the stochastic process of the order that you wanted. And then you compare the calculated stochastic process, the PDF and also the ACF with the exact ones to calculate its L1, L2 loss, for instance, and compared with the target one. With this loss function, you update the parameters in the LSTM cells and also the multilayer perceptrons, which allows you to basically train the neural network. So as I just said, the most important feature of this new architecture is that we use statistics to train the neural network, which basically is saying that what we're doing is that we are not seeking a pathwise convergence to the stochastic process. We are seeking a convergence in terms of moment and also in terms of probably the equilibrium probability measures. And also, we use LSTMs as a basic modeling modules of sign instead of a multilayer perceptrons to model as a basic modeling modules here. And also, as you can see that different from neural SDE, sign is an entirely equation-free model. No matter it is we are not using any equation in terms of the loss function. We are not using any kind of equation in the model. So it's just entirely equation-free. And actually, this equation-free feature brings us some good properties, which I'm going to show. In fact, what I can see right now is actually it helps us to learn actually a stochastic time propagators for the dynamics.
Johan, can you say something about you say L1 or L2 loss for the ACF or for the PDF? Can you say something about the type of norm that you're using?
Yeah, the norm what we're using, yes, is so it actually, we tried several options, and it finds out the results are pretty much the same. I think what we use is just mostly the L2 norm, which basically guarantees you have an overall good approximation of the PDF, for instance, the PDF, and also the L1 norm, which somehow bounds, the maximum differences between the PDFs. We just use these two norms, but I think maybe other norms works as well. I'm not, we tried several ones and then found out these two is sufficient for our research. So we just choose these two.
Because there's other work that, for example, for GANs, gamma divergence, interpolating norms, and so on, it becomes really important which norm in stochastic systems. For example, Mark Katsoulakis and others, and Paul Dupuy here have a paper on it.
For that part, I'm not, quite familiar with the literature, but the thing is, because the statistic that you calculated, which basically deterministic function, you have no randomness here. So I think any kind of norm would be, as long as is used to to help you to approximate some deterministic function, it would be sufficient. So so we didn't do too much exploration in this regard.
And how many moments would you consider? Because you have normal covariant systems.
Yeah, that's an interesting question, which I will comment in the application section.
Okay.
Yeah. So, all right. So the architecture of sign I already presented, but there are also several. I think training tricks for sign, which I think is important because we are handling stochastic dynamics. So first of all, sign is trained in batches. That is because this is what it requires, because we need to take an example of a trajectory and calculate the statistics like the correlation function or the PDF. So you have to do it in examples, okay, in batches. So and also in order to reduce the calculation loss, for instance, calculation of the loss function, what we do is we design some randomized algorithm. We randomly choose points of different legs, like for most of the cases, 20 of them in the whole domain. So the reason why we need to do it, because we'll use this sign to generate a very long time trajectory. So if you calculate it, for instance, with finite steps, okay, in a rather long time, your computational cost will, grows, very fast. So what we do is we run for each iteration, we just randomly select, for instance, 20 points in the PDF or ACF, and then we'll compare it. Because you somehow selected it randomly, so the computational cost is somehow controlled. Well, but in the meantime, you also guaranteed some, the accuracy of your approximation. So this is also an important trick that is worth mentioning. And another one to guarantee that your training result is good is you need to update your white noise input sequence at fresh at each iteration. So why this is important? That is because you want simply the reason is the neural network basically created a transformation of the stochastic process, which is Gaussian white noise, into some, for instance, some colored stochastic process. So because your training is actually this type of transformation, which is deterministic, by the way, nothing random here, because neural network is still deterministic. So you want to avoid the situation that you always use the same type of white noise sequence, and then you get a very large generalization error. So this is another trick, and an actually very important trick. So you have to fresh it at each iteration. So, and for the case that we studied, you'll find out at the computational cost for the sampling of Gaussian white noise is not that large. Another one is we designed some validation sequence, which is the length, 800 of them. This was used to monitor the training error and to avoid overfitting. So these four are most important training tricks for the statistics for the neural network. All right, so let's see the several applications of this, applying this to models of stochastic dynamics. So the first one is a very toy example, which is equilibrium Gaussian dynamics governed by the Ornstein-Uhlenbeck process. So the OU process is given by this very simple linear stochastic differential equation with a modern parameter theta and sigma. So what we do is we know that in the statistical equilibrium, this OU process will give you a stationary Gaussian stochastic process, which have the equilibrium probability memory is Gaussian, and also you have an explanatory decaying correlation function. So what we do is we just use the equilibrium probability density function and the correlation function of the xt. So this answers George's question. For this very simple Gaussian process, you don't need a higher order. And actually, because it's a Gaussian, only the second order would be, it guarantees all the information that you learn is actually correct. So you don't need to higher order. So just one order would be enough. You use these two to design your loss function, update the parameters, and eventually what I show at the left-hand side is simulation result of sign. The first figure is just compare the simulations, the trajectory that you obtained with sign, and also the one you obtained from MD simulation. And as you can see, we do not have pathwise convergence. And this is not something we seek. So what we seek is actually the convergence in terms of the moment and also the probability matter, which is shown at the bottom. So we can see that it actually captures the exact PDF, which is the Gaussian function very well as the time autocorrelation function, which exponentially decaying. And actually, you can see that because we use so many tricks in terms of the training, we'll be able to guarantee that the training error and the validation error of the sign is decays at the same rate, which is make it actually very stable and avoid these overfitting issues. So the sign architecture that we use to simulate this OU process is also very simple. We only use two RSTM layers, and we only use one hidden state actually. Because you only use one hidden state, you no longer need that MLP layers. So this is very simple architecture, and the training is also very, very simple. So this is the first example. So the second example can also be viewed as a toy example, although it's slightly more complicated. This is an example of a non-Gaussian dynamics governed by the Langevin equation. So this is Langevin equation for a single particle. And because the potential force here, this UQ have a fourth order term. So this is the dynamics for the Q part. For the position of this, Lagrangian particle is no longer Gaussian, so it's non-Gaussian. However, in the statistical equilibrium, is also in the statistical equilibrium, Although it's non-Gaussian, but it's also stationary. So this is what we want to. We do exactly the same as before. Wanted to assign the model to simulate the dynamics. So you can see this is sample trajectory. This is the arrow plot. And this is approximation of the equilibrium probability density, which is no longer Gaussian, which is governed by the equilibrium probability density for the Langevin dynamics. And also this is ECF. So as George also mentioned, because you no longer have a Gaussian dynamics, so here we just impose another second order correlation functions into the loss, include that into the loss function in order to capture its high order information. So this is marked as red here. And the reason why is because we're handling non-Gaussian dynamics. So, only the second order information is not enough. So you can, what we do is we add a fourth order. You can similarly add, sixth order, seventh order, et cetera, et cetera. It will help you to further quantify the stochastic process. But for most modeling, purposes, including the second order would be enough. So this is what we do. And then the sign architecture is exactly the same as the previous case. And actually, because you added high order information, actually this already, with this one, you already can guarantee the second moment in terms of it's actually convergent, in the correlation function is convergent. So this is already better than some of the established methods, for instance, the generalized component-level expansion, because most likely it can only guarantee your second order moment is convergent. This one, you can numerically at least guarantee that the fourth order moment is also convergent. And because we have the Parmos-Maillard expansion exists, so basically it tells you that you can include as more as you want, the correlation functions of higher orders, which help you to get more and more accurate approximation to the exact start of the process that you want to model. So I think this one is already show some modeling advantages for the from the sign model that we rented. Okay, so the third example is a more practical example that we use it to simulate the rare events. So the so-called rare event, or is often a concept from the chemical reactions. So rare chemical reaction, like what I show here, is a chemical equation for the the water self-ionization. So basically, you have two water molecules decomposed into one hydroxide and also another hydronium. So this chemical reaction in real water happens in a very low rate. So normally, using molecular dynamics simulation to simulate such a rare event is very computationally expensive, because you need to run the simulation for a rather long time in order to capture enough these transitions between these chemical reactions, in order to calculate something you want to know, like the chemical reaction rate. So here I just show a very very simple modeling for this kind of chemical reactions using the Langevin dynamics in a double potential well. So this well, this V function, this potential well have two modes. And you can imagine that this two mode just corresponds to the left-hand side and the right-hand side of this chemical equation, which corresponds to one side. One side corresponds to one state of this chemical reaction. Another potential well corresponds to another state of the chemical reaction. So you can think of, we have an imaginary particle. It gains through thermodynamic interaction with the environment. They may gain some enough energy to cross this barrier, this energy barrier, and hop from one side to another one. So this would basically simulate the transition between one chemical state and another chemical state. So the forward arrow gives you the forward direction, and the backward gives you the backward direction. So this is a physical scenario here. So that's, for instance, if the potential well that you can see that separate these two potential wells, this energy barrier is high enough, you can see that this particle is very hard to just go over it. So for this kind of case, you have a rare chemical reaction. So what I show the left-hand side is just the simulation for the dynamic system I just mentioned. And you can see that the transition between these two states, one and the negative one, happens in a long time scale in a very low rate. So this is the situation. And what we want to do is use the recurrent linear, so the sign model that we developed to develop a surrogate model for this kind of chemical reactions. And then we use this one to fast generate simulation trajectories to do Monte Carlo simulations, and then with that to calculate. So this will save us, computation. It will save a lot of computational costs. So, and this is a motivation for the research. So specifically, what we do is we just collected a short time trajectories of the transition dynamics that we discussed. Actually, it can be very short, like t equals to 0 to 40 is actually what we do. And then with these 400 trajectories that we collected, we just calculated the loss function, their PDF, and then we use that statistic information to train the neural network, which we expect to represent or somehow to simulate the transition dynamics. And the simulation result is as we're shown here. And actually, because you collect the data in a short time period, and then you can use, once you learn the model, you can do time extrapolation to generate the long time trajectories. So what I'm showing at the top left is basically the long time trajectory generated with sine. The blue one is the simulation result with MD simulation. And what this orange line is the simulation result that you simulated with sine. And then you can see that it actually captures this transition between two states very well. So this is it. And you can do evaluate its probability density function, its time autocorrelation function. And because your potential will have two modes, your PDF also have two modes. And also because you have a rare event, your time autocorrelation function actually decays in a very slow rate, which it has a long time tails. So it's actually things, so which make the dynamics complicated. So the first role was basically just show some very intuitive like explanations to see actually science can really help you to capture this dynamics. Then what we want to do is how can we evaluate how good this model really is quantitatively. So what we do is we use this sine as a surrogate model, and then we sample many long time trajectories, and then we calculate the transition probability between one whale to another one. With this transition probability, you can actually accurately evaluate this transition rate, which basically in which rate the particle hops from one side to another one, correspondingly, so in which rate the chemical reaction happens from one state to another one. So, so this is the second row, just show the simulation result. So what we have found is actually the sine model can give you a very accurate evaluation of the reaction rate as low as 0.02. So this is the simulation result we have. So it is worth mentioning that because the dynamics of what we are simulating is really complicated, is definitely much more complicated. So what we have done is we use 2 LSTM layers and with 25 hidden states. And because you have multiple hidden states, you need to use MLP layer to project it. Yeah. So yeah. Thank you, Yanis. Yeah. Yeah. All right. Okay. So so this is the main simulation result that we have done, and then we wanted to do some post-processing. Yeah. Thank you, Yanis. Yeah. The post-processing of how well this sine model really is. So what we do is we found that the sine model has the predictability. It also shows numerical suitability and also shows a numerical convergence. And I will explain these 3 terms one by one. So what is predictability? As I just explained, so for this transition model, we only collect the data in a very short time period. And then we do extrapolation. So we need to evaluate how well this time extrapolation really is. So what we do is to compare the time autocorrelation functions. And we can see that the first figure, we only collect the data from 0 to 40. And the second one is 0 to 70. And the third one is 0 to 100. As you gradually increase the time that you collect the data, of course, you get a better result. But even as time as short as 0 to 40, you already have some good approximations. So this is the predictability of a sine. So you can use it to predict the long time dynamics, to extrapolate. And then we wanted to evaluate how well this stochastic trajectory you generated, especially how stable that really is. So by stable numerical stability, what I mean here is because we wanted to simulate some transition dynamics, we wanted to see the stochastic trajectory that you generated, especially in the long time, whether it is numerically stable, you have you get some stable probability density function or time autocorrelation function, and the result is yes, you can get a very good result. And last one is numerical convergence. So the numerical convergence for this case is means the following, because eventually what you're doing is to train a neural network, and the neural network you use some randomized optimization. So and then you truncate it and you stop the training after you obtain some numerical accuracy. So this basically means that for each training, your neural network that you finally obtain will be different. So what we want to do is whether you have some consistency in this different kind of model that you have, okay, whether you have the consistency, and how to do the consistency test is whether it generates the correct dynamic behavior that we wanted. So this is actually what we do. So we trained like 10 candidate models and use this candidate model to produce so-called 95% confidence intervals, and then to compare how good different kind of optimizations give you how good the result, whether you have some consistency here, and find out is actually indeed the case. And with this is somehow we obtain the numerical convergence here. Another thing I want to mention is that the sign model that we train actually define a time cosine time propagator for the stochastic dynamics. And this is directly related with the equation-free feature of this neural network model. So why this is a good thing and why we have the case? That is because when you train the neural network, you use the time trajectories of your data that you collected. You don't need to really stick to the time trajectory that you really obtained from, for instance, MD simulation. For instance, from the MD simulation, you obtain a trajectory which have a step size delta t equals 0.001. But when you train the neural network, you can use a filtered stochastic trajectory with delta t equals 0.1, 0.2, 0.5. So this becomes a time cosine trajectory. You use this time cosine trajectory as your target stochastic process. Then when you train the neural network, your neural network automatically gives you a time cosine stochastic trajectory. Therefore, sign naturally defines a time cosine integrator for your stochastic dynamics. Why this is important? Because if you want to simulate a red event, which happens in a very long time scale, so this will make your simulation extremely efficient. Just for instance, your sign have the time scale which is 0.5, and your MD simulation's time scale is 0.001. Therefore, immediately you get 500 times faster in terms of sampling or generating these stochastic trajectories. So this is a huge computational benefit for this model. And the natural thing, so what we have shown above is actually a simulation result of the sign, the trajectory we generated with different kind of cosine time scales. And actually, all the previous numerical simulations that were just shown is actually have been done in the cosine time scale delta t equals 0.2. So, so why this is closely related with the equation-free features, and why this is also closely related with function compositions. I think I can give an intuitive explanation using the classical Runge-Kutta method. So the Runge-Kutta method, in essence, actually is function composition. So many people may not have noticed. So this is a Runge-Kutta fourth order method. So for instance, if we wanted to calculate K2, K2 actually equals to the F, the inside is Y1 plus H, is the step size, multiply K1, which K1 is also the derivative, which is Ft and Yn. You can see that this already have some function composition structure. So F compensated with another F. So you further expand this to rewrite Yn as an update for Yn minus 1. So you can see that you can continue this process and you get a compensation of compensation, compensation of compensation. So this is the reason why we say the Runge-Kutta method naturally have the function composition structure. And if you expanded it, as I show here, to the second order, you can see that the input of this right-hand side is actually Yn minus 1, and output is Yn plus 1. So you basically get a time cosine. You can imagine that if we continue this process, for instance, you get a very long expressions of using this Runge-Kutta method, and then you can use Y0 to update the dynamics of Y10. So you get a cosine time integrator. So I think what we do implicitly using sign is doing something similar to the Runge-Kutta. You use very complicated function composition, and which eventually gives you some cosine time integrators for your stochastic dynamics. So the last part is what we want to mention is, because with the exploration, we might think in the recent years, there is some paradigm shift of mathematical modeling. So traditionally, what we do is mostly equation-based reduced order modeling. So we normally start with some microscopic dynamics given by molecular dynamics or quantum dynamics, and then we perform some cross-grinding to it to get some mesoscopic and then macroscopic dynamic model. So the universal form of the classic modeling is used by this, you can think of this PDE. So with the right-hand side, F can be derivatives, can be functions, can be stochastic, you name it. And you have some modeling parameters. However, in the equation-free reduced order modeling, especially use the neural network architecture. So you have the universal form will be function compensations with different layers of a function compensating with each other. And then you have modeling parameters. So I think personally, with the exploration that we have done, that this new form, universal form of the model with using function compensations is very powerful in terms of representing complicated dynamics. So I think there is definitely more that we can think of or expect this, this equation-free framework, and also especially using the neural networks. So sorry, I used a little bit more time. I'm very sorry. So basically, let's do a very short summary of the research that we have done. So we introduced the SIGN, which is a simple equation-free machine learning model to learn stochastic dynamics. We have shown that it can model Markovian, non-Markovian dynamics, and also for non-Gaussian and also the Gaussian dynamics. So the Kramer-Moyar's expansion guaranteed that you can actually get higher order convergence with SIGN. And also an important feature of SIGN is actually it defines a cross-blind time integrator, which is suited for some simulations like the RAY-UAT. So for several principal extension with this framework is, for instance, we can develop a multi-dimensional SIGN and evaluate SIGN to learn some stochastic PDE. We can also design, for instance, consider some attention-based SIGN instead of an LSTM-based SIGN. We can also apply the similar strategy to quantum many-body system. I think that's roughly it for my talk. Thank you very much for your attention, and also thank you very much, especially George, for giving me this opportunity to present our work at a Crunch seminar.
It's a great talk, very informative. Any questions for Yuan or Changho? I think Changho will answer all the questions since Yuan gave the talk.
Sure.
Yeah, I see Felix raised his hand. Felix, go ahead.
Yeah, hi. Yeah, thanks. Thank you for the talk. I have one question regarding the loss function as well, because you showed briefly that you need quite a large batch size, right? Because as far as I understand, you try to match distributions on this one slide very early on. Yeah, here, yes. Yeah. So this slide is fine as well. Yeah. So you compare PDF.
Not just PDF, I think also SCF, right?
Or SCF, yes.
Yeah. No, not all. Both, I think.
Both. Mm-hmm. Yes. So is it true that you need a large batch size so that your approximation of the PDF and ACF are good?
Changho?
You go ahead.
No, Changho, you have to answer. The professor has to protect the.
Yeah. So it's really like how to approximate. I mean, so how to characterize our stochastic process. That's really the most important thing, because this approach is our overall goal is like how we can generate construct like a stochastic path generator. So our goal is like how we can really develop a surrogate model for other approach. So yeah, so ACF and PDF, we believe for at least for the stochastic process we are interested in. So they can be well approximated by like ACF, and also like for non-Gaussian process, we realized. I mean, so we thought like actually we realized that actually PDF, including PDF, improves the quality a lot. So and batch, so we need batch because we eventually we need to approximate the statistical property. So we need batch, and yeah, I think that's the overall our like the reasoning behind our construction.
Interesting. Okay, so in every iteration, essentially in every training step, you need a large or you need an approximation of this PDF.
So basically we really like let's think about the batch as a representation of your so it's like a collection of trajectory, but we can just think of this as a representation of the ensemble of the stochastic process.
Right. Interesting. Because I mean, maybe I can link this in the chat, because Yanis and I have done sort of an orthogonal route where we don't want to approximate the PDF in each step, but we want to do this pointwise. But then, of course, we will not get a good approximation of the PDF specifically, right? So we train from a given point to the next point, knowing what the PDF will be. But just
so what do you mean by
point-wise.
the point? You mean time point?
Yeah. So just one state and the next state in time, without knowing the distribution of points over the space. But from what I understood, you need the distribution, right? You're showing it here, and you're not even considering individual points in the training. You literally just compare PDF and ACF.
Yeah. We basically, just training it in Zambo and compare it in Zambo.
Right.
Yeah. And also, maybe for your case, slightly different. For our case, we primarily focus on the equilibrium dynamics.
Right.
So the PDF will be unchanged. So, if it.
But on that point, because and sort of you can have something not as precise as Felix with time-wise, but actually, since you have very short duration of the burst, you take bursts of these ensembles, you can actually have a slowly varying, a non-stationary process.
Yeah.
It doesn't have to be a stationary process.
Yeah. That's true. I agree.
So also, in my opinion, so we kind of first we start with like Euler Maruyama. So kind of we just want to approximate kind of like the transition between points. But if we impose the overall, the eventual equilibrium distribution PDF, then I think it may help the long time stability thing. So because we want to have a like equilibrium thing.
Of course. Yeah, you're essentially training towards this, right? Like you want this to be the goal of your training. Yeah. Nice. Thank you.
Thank you.
Any other questions for Chanho or for Yuan?
Yeah, I see. Okay, go ahead.
Can I ask you a question? I'm Ting Wei. So
Ting Wei, not anymore from Brown, from UCLA.
next month from UCLA. This month is a gap.
Okay.
So thank you for the interesting talk. I just want to have a question about the training process of this. On this slide, you compare the PDF and ACF, and then you do the L1 or L2 loss, right? My question is, if you input some white noise, then if I understand correctly, you get some ensembles, then do you need to have some kernel method to get the function of the PDF, and then you take the L1 or L2 loss then, or do you need some other techniques to compute the loss?
Okay. Yes, that's a good question. Yes, we use the kernel density estimation to estimate the PDF.
Okay.
That's what we're using. And the histogram is not used here because histogram is not differentiable.
It will not be good. Yeah.
Okay.
Goes back to Xiaoyang thesis.
Okay, thank you.
Yeah, sure.
Zogren, you have a question?
No, I see someone has a question.
Okay.
Yeah,
Costas from from Italy. Yes, Costas.
Yeah, thank you, George. Thank you for your talks. Very interesting. Actually, following up the comment of George for stationary, but I will go one step ahead. So you're considering the statistical properties of the noise, like not changing, right? But we know that many processes, especially in financial time series, these things change in time. So you can go from color noise to white noise and this thing. How you deal with that?
Okay, so I will try to answer that one. So, okay, let me put it this way. So we know that right now, a lot of stochastic dynamic systems, stochastic ODE, PD or ODEs, we will converge on equilibrium state eventually, for a lot of them. So so right now, what I can tell you how we train the neural network. We train the neural network is we basically treat it like an ODE SDE solver, and then we train we give the input, and then we actually burn out. We exactly like we do in MD simulation. We burn out the first, 0 to 1,000 this time, is time trajectories, and we basically assume that these, the sign will eventually converge to equilibrium state. And then we compare. We only use the data in that part to calculate the equilibrium PDF and ACF. So what I can argue is, although I haven't tried, is that if the thing that you want to model eventually will converge to some equilibrium state, and then your sign models guarantee that your model, our model, sign model also converts to exactly the same equilibrium state, I think it also captures in a great sense, although don't take my word 100%.
Yeah.
In great sense, in the short time, non-equilibrium transition behavior will behave similarly. Although maybe you need to do more simulations, and also in order to quantify this non-equilibrium transition in a better way, you need to include more, for instance, time-dependent correlation functions, for instance, for this kind of cases. But I think it's definitely doable and worth trying.
Yeah, that was also what I was thinking. Yeah. Okay.
Yeah. Thank you. Good question.
Let me add a few more things. So I think this modeling strategy has like some extensibility, but the problem is like if we really consider generalized stochastic process, then how can you characterize the stochastic process? So that's a bit like so if we can characterize something, then we can include that one in the loss function, but it may not be very clear. So that's one thing.
Yeah.
But in terms of like a multi-scale modeling approach, then we can always consider some type of a local time, like a time separation. So, and then for this type of, so we want to use this one as a surrogate model for microdynamics, then we can kind of assume, we can always assume like a local equilibrium approximation in some sense. So in that sense, we can learn this one as just the equilibrium process, but maybe slow varying parameter.
That's what I said. Weekly non-stationary.
Yeah.
All right. Okay. Thanks. Thank you.
Changhua, I saw, we model these ACFs with exponential and cosine, right, e to the minus x cosine, like that's what we did with Eric Darv and Jen Lee and so on.
Mm-hmm.
And so it just basically two-parameter thing, but it was actually much more complicated. It has the cosine. Most of the ACFs that you show, it was just an exponential. I think there was only one case, the bistable case, that because if you do like you had, for example, the proteins, the polymers, and so on, the ACF is like we see on this picture, the top one, more like that. There's an exponential, and then there's a goes negative, and then you have the cosine and so on. Why did you all choose? Why did you choose all the ACFs to be just a simple exponential decays, which I could draw by hand?
Yeah. So actually, when we start this study, actually I provide that example. Like if we like extend the variable, then actually it's a Markovian. But if you just look at the small thing, then so actually the first example I provide is actually like it's more like a cosine. Exponential cosine stuff, but just for so maybe in this paper we just want to be just like simpler one, but maybe like we should have a
this one was good. This one I like this one. Yeah,
this one is something like that. It's not
exactly. Yeah, exactly, because if you have bonds right in the protein or in the polymer, you get that type of multivariate dynamics. But I saw that was very impressive that you actually, although the PDF is not doesn't have really heavy tails in the output. It goes back to simple, because you can see in time it goes to 0. So
so for PDF actually by reproducing by modality is much more complicated than
there's a way to do that with, if you do it
not really
in the latent space, you can simplify, but I would suggest for your papers you can plot the PDF at time t equals 0.5. 2.5 time t equals 2.5, because you show the beginning and the end, which is boring, but at 2.5 and at 5 is interesting. So if you get a comment like that, that's probably me, the reviewer.
Thank you. I record that. Thank you for the comments, George. Yeah.
But great work. As I told you, one of my former postdocs already has used it for DPD simulations. So he's learning the fluctuations from the bubble. We did this bubble with DeepONet, so now he's learning the fluctuations. We could learn the fluctuations before. So that's how I got to know this, your paper. So congratulations.
Thank you. Thank you.
It's me. Can I ask one more question?
Yes, Lulu.
Yeah,
Yes.
Lulu, yes. So in my understanding, so the main application of this, once you train a network, you can use it to easily generate lots of samples, right? That's the main target of why this is useful. But if we do this, but the loss function is only the ACF or PDF, how you guarantee the samples you are generated is meaningful or is correct?
Okay, so who is asking, by the way? So
Lulu.
Okay, Lulu. Okay, so yes. Okay, so here is you know, you can quantify stochastic process in by stochastic characteristics, right? Any kind of stochastic process. So if for any kind of sort of process you want to model, if the one that you wanted to finally use it is the statistic property, for instance. What do we want to do, like the transition dynamics models? We collected the correlation function, and what do we do? We actually interested in this transition probability, which is another PDF, different type of PDF. So we are interested in the statistical properties, and we wanted to use it to predict another stochastic property, as long as the statistical properties that you want to predict or calculate or use this surrogate model to approximate is well captured, and then that's good enough for our modeling. So. And also, this also saying that, you can add, as I said, as much as you want into the loss function of different kind of characteristic. You can add a higher order, correlation functions, no matter what it is. You just add it in there, as long as depends on what you want.
Johan, I think the question here, maybe Lulu could have asked is, should you always have, or should you include skewness and kurtosis, flatness in your for intermittent dynamics in your loss? Because if you have intermittent dynamics, real intermittent dynamics, you're not going to get unless you get to the fourth moment.
Oh yeah, highly possible. It depends on the application. In the current one, our dynamics is not that complicated. But if you, for instance, you use kind of higher dimensions, you can put this one, as George mentioned, into your loss function in order to get a more accurate model. But like I said, it eventually depends on what do you want to use this model for, what kind of information you want extracted from this reduced order model.
But in theory, you need an infinity number, right? Otherwise, it's always non-unique.
Oh yeah, totally. It's non-unique because you're handling mostly non-Gaussian stochastic processes. So it depends on what you want. So if the information that you quantified, the correlation function, for instance, is enough for the one that you want to simulate. For instance, this transition probability. What do we train this neural network? We use the first order correlation function, second order correlation in the PDF. In principle, you can add more, but this is already enough for to capture the most important physical quantity that we wanted to calculate, that is transition probability. And then that's enough. But of course, the the neural network, the stochastic process you generate is not unique. That's for certain. But although it's not unique, but we already have enough, unique in enough way that you already.
No, so basically, my question is, do we need the samples or not? Or do we really care about the samples or not? The samples.
Samples.
Basically the generator of the samples are generated. So
we use that. We use the samples.
But it's in theory it's not correct, right? Or we cannot guarantee it's correct.
Cannot guarantee it's unique.
No, even it's not correct. I think.
I think he's asking again if the individual paths, if they would be useful.
Individual paths. I don't quite think so. For this, because it's training in ensemble, it's outputting ensemble, and we care about the ensemble. So
yes, that's my question. So the individual paths can be totally incorrect, although all the characteristics is correct.
Oh yeah, it is possible. Yeah, I agree.
Yeah, so I think it's more like a strong convergence versus weak convergence.
Yes.
In order to check strong convergence, then you need to provide a pure random realization, like a Wiener process.
Yeah, that's my follow-up question. So if I cannot guarantee the individual path is correct, why do I have to output the individual path? I can directly predict these characteristics. Why do I?
So I have the following question. It would certainly make sense, separately from learning anything, to have a data-driven test for deciding whether this is an SDE with Gaussian noise, it's an SDE with Gaussian and Levy flights, it's a qualitative characterization for the noise. I can understand almost immediately what it would be to estimate. How can you test the hypothesis that your data come from an SDE with Gaussian noise, let alone what is the particular form of the diffusivity and the particular form of the drift? This sounds simple, but I haven't seen it somewhere in particular. Does anybody often know? Like, I have a time series. How do I test that, separate from learning, that this is in the class of state-dependent drift and diffusivity plus Levy flights? I don't know, George, have you seen this somewhere?
From a single, from multiple trajectories.
No, you have a bunch of
some stuff that we're doing with Yang Liu and Daskalakis has this flavor, because we're looking at both, trying to identify Levy processes.
I understand. I'm not so much asking for the identification of the Levy as the test that it can be fitted with, that it has Levy. I understand also implicitly, if you can identify a Levy, then you can say it's well fitted. But I'm just wondering if there is what's the right hypothesis, like design of simulations for testing the hypothesis separate from learning the equation. That's the thought.
Yeah, I don't know. I think Matthew Harrison was here earlier. If he's there, he would know. I don't know.
Okay, thanks.
Okay, good discussion. Thank you very much, Chang-Ho.
What happened with the first guys?
No, he's here.
Okay, good.
He's here, so we're gonna have the talk. Maybe he can share, and then Jogren will introduce him and share the screen. Yeah. So all stochastic today.
Yeah, great.
Stochastic and uncertain, literally.
Okay, so let's move to our second talk. Our second speaker is Chris from Imperial College London. Chris is currently a Chapman Fellow in the Department of Mathematics, and his current research mainly focuses on the interplay between graph analysis and several machine learning sub-areas, including deep learning, kernel methods, and Bayesian inference. Before joining Imperial, Chris obtained his PhD from the University of Oxford. So without further ado, Chris, welcome, and you may want to start.
Hi. Yes, hi. I am joining also with my iPad, which is named the Niels iPad for some reason. I haven't stolen it, but if you can grant me access as the...
So which equipment you want to share your screen with?
I think you need to grant me access on the iPad to share the screen. I get message only the host can share in this meeting.
Sabdala, are you there? Could you help me with that? I don't have access to assign co-host to Chris.
Hi.
So you can search iPad in the attendance.
It's called Niels iPad. Yes.
Niels iPad. Yeah.
It works.
Still not.
Oh yeah. I think you already have the access. Could you give it a try?
Yeah, thank you very much. Yes.
Problem.
Thank you. And I apologize for having misunderstood the time of my talk.
No worries.
Thanks God there was the previous speaker was available. Thanks to the previous speaker as well. Right, so yeah, thanks for the invitation and the kind introduction. So just a little question. Do I have an hour, or do I have, how much time do I have?
Yeah, you can go with one
Yeah,
hour.
you have an hour, yeah.
Okay, you tell me when you want me to stop. So I'll start with some not very deep remarks, but hopefully correct. So differential equations are everywhere, used everywhere throughout science to model all sorts of things. Very recently, or not very recently, but over the last decade or two, deep learning and neural networks have invaded and revolutionized technology. And there are deep connections, it turns out, between these two areas. And part of my research is about understanding these connections, or some of these connections. And the interplay between the two goes both ways. Neural networks can be, or most neural networks can be interpreted as discretization or approximations to differential equations. And this is the direction that I will focus my talk on today. But there is also the other direction that is very popular these days in machine learning research, which consists in using neural networks to solve complicated high-dimensional or even possibly infinite-dimensional differential equations. And my area of sort of technical area of research, which is rough path theory, turns out to provide a robust solution theory for some classes of differential equations named control differential equations that are driven by signals of arbitrary roughness. And I will try to explain without details, but at a high level, some of the insights that come from this theory in today's talk. Okay, so I'll start with something that probably all of you are familiar with, and I'll go through it quite quickly. So an example is, a very simple example of connection between neural networks and differential equation, a residual neural network defined recursively in this way. It's quite easy to be related to the discretization, in this case, a Euler discretization of an ordinary differential equation where the vector field f is replaced by a neural network, which corresponds in this case to the residual block of the rest net. And this was, let's say, the simple yet powerful observation done in the neural ODE paper that became viral. So, of course, more generally, if we forget about the neural architecture and we just consider the differential equation, there are many different ways of solving numerically such an equation, and each scheme would yield a different neural architecture. And speculatively, one might argue that, and actually empirically, it can be argued that the closest a neural architecture is to a discretization of a differential equation, the better the performance. Okay, so this, so what I'm really interested in is designing, let's say, neural differential equation models to consume sequential data. So, of course, the go-to, or definitely the most well-known neural architecture to consume sequential data is a recurrent neural network. So here I wrote a slightly different version, the residual version of a recurrent neural network, just to make the analogy with, well, not the analogy, but the analogy with the corresponding differential equation easier. So this is a recurrent neural network. The continuous time version of this RNN, after some little manipulation, let's say, is in all generality can be written in this form. And this is the kind of equations that rough path theory, and not just rough path theory, dynamical system people like to study. So this is a controlled differential. We call it a controlled differential equation, where you have an infinitesimal displacement of an external signal of information that interact with a nonlinear system that is represented by the vector field in order to provide an infinitesimal response upon this interaction. And at the bottom of this slide, you can see a very simple example of control. On the left-hand side, this is a two-dimensional Brownian motion that interacts with a stochastic Lotka-Volterra system to produce a response, so another signal that is on the right of the picture. Okay, so neural control differential equations is, I mean, it was implicitly thought, I mean, it was that the vector fields of this control differential equation are parameterized by neural networks. And the neural control differential equation is exactly that. It's a control differential equation where the vector fields are unknown and are parameterized by any neural network of choice, really. And
can I ask you a dumb question? Is this equivalent to a Langevin, more inclusive than a Langevin, less inclusive? How does it compare with the usual Langevins that we like to write?
So I'll get to SDEs later on, but yeah, this the Langevin is an example of a control differential equation. Yes.
Okay.
Yeah. So so neural control differential equations have been used traditionally they haven't been around for a long time, a couple of years, but the main use case is inferring functions on time series, so time series regression, time series classification, and so on. And the way they operate is quite simple. You start from a time series, so a discrete sequence of observation. Then this time series is embedded into a continuous path via an interpolation scheme of choice. And depending on the applications at hand, one might choose to use a different interpolation scheme rather than another. But the important thing is that the time series is embedded into a continuous time path. So it's really a function from a time interval into a d-dimensional vector space. And then the neural control differential equation simply evaluate the solution of such a control system, like written in the middle of this slide, driven by the continuous path interpolation of the time series. And the output, so the solution of this control differential equation is the response. And then depending on the application, you might want to take the value of the response just at final time, or you might be interested, for example, in the full trajectory. For example, for a sequence-to-sequence or a path-to-path task, you might be interested in extracting or in querying the full trajectory out of this control differential equation. And okay, so the examples of signals that can be processed by this kind of models are, you can imagine position of a pen traced on a paper. That would be a two-dimensional curve, patient hospital records, financial markets, stock prices, and so on. So this is quite self-evident. So there are plenty of details that I won't be able to discuss today. In particular, I will touch upon memory-efficient backpropagation perhaps later on. But there are one of the main motivation for, or perhaps reason for success of such differential equation models is the ability of performing a memory efficient backpropagation through the model. Of course, there is a naive way of doing sort of immediate way of performing backpropagation through such a differential equation model, which consists in simply starting from the numerical scheme, so starting from the discretization of the differential equation. This discretization is built out of simple linear algebraic operation, and therefore there is absolutely no problem in backpropagating through the differential equation solver.
It doesn't have to be linear, it can be an implicit integrator.
Sure, yes.
Yeah.
I agree. Yes, but the idea is that I will touch upon later on. But the idea is that the output of the differential equation is fed into a loss function, and the goal of backpropagation is, of course, to compute the gradients of this loss function with respect to the parameters of the model. Now, it turns out that if the model is a differential equation, this derivative is the solution itself. It is the solution of another differential equation, explicitly defined in terms of the original one. Therefore, the backpropagation can be done effectively and efficiently in terms of memory by solving an augmented system of differential equations. And I'll give the example of an SDEs later on. Anyway, so other things that I'm not going to discuss are choices of the vector fields in order to ensure existence and uniqueness of solutions to these dynamical systems. Of course, there are a lot of assumptions that have to be made on the vector fields, and how to impose, like for example, Lipschitzianity, how to impose these assumptions on a neural architecture is very important to keep in mind. The interpolation scheme, as I said, the first step is to embed the discrete sequence into a continuous path. And for example, if you are dealing with the simplest way of doing so is by piecewise linear interpolation or piecewise affine interpolation, if you want. But if, for example, you're interested in online predictions of some sort, of course, piecewise linear interpolation is not possible because at time t, you have no idea where the next point will be until it arrives, until the information arrives. So in that case, on piecewise constant interpolation is perhaps a better choice. Numerical solvers, as you can imagine, there are more than, I don't know, 100 years of development of numerical analysis for solving differential equations that can be leveraged to evaluate this kind of models. Scaling to long time series, this is also quite important and complicated to deal with this kind of models, but it's possible to find solutions that are also based on some ideas of inspired by rough path theory that, again, I don't have time to discuss. And finally, the software. So the software has been one of the main sort of development in this field. It's amazing how quickly different flavors of implementation for these models in Python-based, though, have been, as far as I know, have grown. And no matter if you're a PyTorch person or a JAX person, there will be a very robust implementation for you. Right. So,
may I interrupt for a moment?
You can, sure.
Yes. Could you close? Is it possible to close the floating window on your iPad? Because it covers the
floating window. Yes. Okay. Yes. Now you can hold on. Now I've opened it completely. Let me share screen. Can you see my screen?
Not yet.
Right. So what have I done? Screen start.
Oh no, there it is again. Yeah, you can move it to upper right or upper left. Oh, okay. And no,
I pushed it away.
Thank you.
Okay, no problem. Thanks. Right. So, okay. So a specific example. So go back to this system. So this control differential equation. So at the core of rough path theory is the idea of making sense of such dynamical systems, no matter what is the regularity, or rather the irregularity of the driving signal. So it was known since, I don't know, early 90s, no, the early 1900s, how to, I mean, even before, how to make sense of solutions of differential equation driven by smooth signals. And by smooth, I mean signals of continuous signals of bounded variation. So of course, there are some technical terms technical quantities to quantify the irregularity of a signal. Holder regularity is, for example, one such quantity. P variation is another one that is more traditional to rough paths. But anyway, continuous paths of bounded variation can be dealt with. So in other words, one can integrate things against path of bounded variation using standard Riemann-Stieltjes integration, which is a slight modification of the classical calculus, Riemann calculus that we all learn. Now, the more the vector, the control signal, so the WT, becomes irregular, the more complicated it is to make sense of what it means to integrate something against such a signal. And of course, in stochastic analysis and the study of stochastic differential equations, well, a lot of theory has been developed to make sense of things driven by Brownian motion, and which, by the way, represents exactly a threshold where the old theory of Riemann-Stieltjes fails. And so because things don't converge when a Riemann approximation of the integral is taken. And so Ito integration, Stratonovich integration, and other kind of integration theories have been developed specifically for Brownian motion. Now, rough paths, what it does is that it creates a framework that allows to make sense of integration against a path, no matter what is the regularity of the path. Yes, and yeah, that's all I will say about that. But I want to, I would like to be more, to sort of zoom in into the use case or the type of the class of control differential equations that are controlled by Brownian motion. So these are stochastic differential equations, classically written in this way. So, you know, here there isn't just, so there are two terms, not just one, but it's quite simple to see how to retrieve the formulation that was in the second slide that I showed you before by simply considering the Brownian. So W here, it's a Brownian motion. By simply considering the Brownian motion with time, so with an extra coordinate that represents simply the time, and writing this equation with a single vector field. But traditionally, the stochastic differential equation have a drift part and a diffusion part. So I'm going to stick with the traditional notation. So the solution here is a priori is a d-dimensional stochastic process, diffusion process, and the driving noise is an m-dimensional Brownian motion. And lots of things can be related to such a dynamical system, especially in finance. And of course, when, you know, in the context of neural differential equations, a neural stochastic differential equation is simply a stochastic differential equation where the drift and the diffusion are parameterized by neural networks. So it's always the same story. Right. So now okay, so let me see, right. So let me skip this slide and perhaps going back to it. So the use case, the main use case for neural SDEs is quite different from the use case of neural CDs that I was quickly referencing before. So as I said, neural CDs, the input to a neural CDs is a stream of information, is data. The input to a neural SDEs is not data, it's Brownian motion, which is not an input, right? So the use case for neural SDEs is traditionally been the one of using it as a generative model for time series. So in other words, the goal is to, you know, it's very simple. You have an empirical distribution X true on path space. So here we're talking about a random variable supported on path space. In other words, a stochastic process. The goal of a generative model on time series data is the one of providing samples, so providing a distribution of time series that is indistinguishable in some statistical sense from the original time series. And crucially, the important quantity to keep in mind here is how one can quantify the discrepancy or the dissimilarity between two distributions on path space, being it empirical or being not empirical. But in the case of generative model, of course, they're empirical. So one of the most important step into building a generative model, at least a la GAN, is to come up or utilize a discrepancy between distributions supported on the space where the data lives. In this case, is time series. So a discrepancy for stochastic processes. This is what we're talking about. And the property that we require from such a discrepancy is this one. So we would like, if the law of the stochastic process X equals the law of the empirical measure X true, if and only if the distance between X and X true is equal to 0, whatever this distance D means. And for the rest, for the rest of the talk, not for the rest, I will have a third part, but for the second part of the talk, I will try to give you some insights on how we can build such a discrepancy. Right, so here is a picture of some generated samples from a rough volatility model and some true samples of the underlying diffusion. Well, it's not even a diffusion in this case, of the underlying rough volatility model. Yes, hello.
I have a quick question. So the probability distribution you mentioned here, can I understand it is like the probability distribution for the whole stochastic process, like the path integral?
Yeah, there is no distribution. There is no PDF. There is no density here because okay, so this is actually a good question. So on path space is an infinite dimensional space. Okay, so there is no Lebesgue measure in an infinite dimensional space. Now the definition of density or of likelihood is the radon-Nikodym derivative of the law by the Lebesgue measure. So when you're dealing with paths, or rather with stochastic processes, it's not possible to make any sense of the traditional law. Well, it's not possible to make easily sense of the notion of density because there is no Lebesgue measure. So you can sometimes prove that there is a derivative with respect to the Wiener measure, but that's complicated. But there is certainly not anything related to the Lebesgue measure because there is no Lebesgue measure. So in this case, all the generative models that are likelihood based, like variation autoencoders, normalizing flows, all this sort of stuff, they they have been applied to the generation very successfully, I would say, in the generation of time series data. But from a mathematical perspective, they rely on a lot of assumptions that sometimes are not really discussed. They work in practice, but whilst GANs, given the fact that they're not based on any notion of likelihood, but they're based on a notion of measuring via discrepancy the distance between two distributions. And of course, there is a way, and many ways actually, to come up with discrepancies between distributions on path space between stochastic processes. And so GANs are, in my view, a much better choice when it comes to generate data on path space, if you're really considering a continuous distribution supported on continuous path space. Of course, if you start to take things time step by time step and discretize, that's a different story. But in the way that, if you think of in this case of random variable supported on a function space, then, this is the, I think it's from a mathematical perspective, is a more robust way of treating things. Then who knows if it's going to work better or not, but at least the maths one can understand. I don't know. Yeah. Thank you for the question. Yes, but of course we can debate all of this whenever at the end or now or whenever we want. Okay, so okay, we need this distance. Okay, we need the discrepancy that measures the similarity or dissimilarity between two stochastic processes. And for me, a stochastic process is really, there are different ways of introducing a stochastic process. Some people fix the time t, and then they evaluate the time t on a random omega from your probability space, and they get a vector. So that's the traditional definition. For me, a stochastic process is a random function. So and a sample is a path. So that's an alternative equivalent view of a stochastic process. So we want to build, just to finish the connection with GANs. So of course, so and neural SDEs. So provided that we have such a discrepancy D that I will talk about in a second, and this discrepancy, by the way, could depend on some additional parameters phi in this case, then the GAN way of generating time series would consist in having a discriminator. In this case, discriminator is a neural SDE that morphs Brownian motion, so the Wiener measure, into a different measure, which is the strong solution, if it exists, of the SDE driven by the Brownian motion. And then the discriminator compares the generated distribution with the true distribution, and there is this the classical minimax game where I think the min and the max here should be swapped, where the generator tries to generate things that are closest possible to the true distribution, while the discriminator tries to tell them apart, and then they reach an equilibrium. So that's the sort of hopefully they reach an equilibrium, and that's the end of the training. But anyway, so the thing that I want to focus on is building this D, and a popular, very large class of discrepancies between random variables is given by the family of integral probability metrics. So this integral probability metrics, basically, what is it? You take a class of functions, curly f, from the support of your random variables to R, real valued functions that are okay, they're bounded and measurable. And then you try to, these are called in the Wasserstein world, are called witness functions, but you can call them test functions, whatever you want. So you choose a class of functions, and then you take this, you define the distance between two random variables to be the supremum over all such functions of the absolute value of the difference between the expectation of f of x minus the expectation of f of y. Okay, and this is quite a generic class of discrepancies of metrics between random variables. Now, the question is, how can we build such an integral probability metric where x, so where the support of the two random variables x and y is an infinite dimensional space of paths? Well, of course, in this case, we need to pick a space of functions curly f that is written in this way, is simply going to be functions from paths that maps paths to R that are measurable and bounded. Okay, so right, and here is where rough path theory can really come in and help. So one way of identifying a space of functions of this form would be using this idea of a feature map. So suppose that I'm given, well, I'm not given, but suppose that you have a nonlinear function f, highly nonlinear. Oops, I didn't want this, but continuous, that maps a path into R. Okay, this is the actual the base object, base function that we would like to represent in an easier way, let's say. Now, this sort of diagram is sort of the essence of machine learning, if you want. I mean, the goal is to try to come up with a feature map, so with a map that extracts some features from the input space, in our case is path space, that are expressive and high dimensional enough so that the action of the function on path space can be approximated by a linear action on the feature space of that the feature map lifts the input to. Okay, so we want this diagram to commute, basically. So a good feature map, I mean, this is not very deep, again, it's a remark, but it is quite important for what comes next. A good feature map will be such that for any path, for any function, f of f evaluated at that path is approximately, and you want this to be arbitrarily close to a linear functional acting on the feature map applied to the path, applied to the input. Okay, so we have lots of examples for Euclidean data, and but for paths, that's where the signatures come in. So rough paths provide a natural feature map for time series, for path space that does this. And I will repeat this universal limit with this universal approximation theorem here. So first, okay, so you're what's this feature map? What's this called? We call it the signature. So you get a path. So this is really a d-dimensional path. It's a function from a time interval into Rd. And the signature of this path gamma is represented in formula. This is the sort of a dry expression or definition of the signature. Is an infinite sequence of numbers that are organized by levels. So you have the first level, the second level, the third level, and so on. And these numbers correspond to the iterated integrals of the path against itself. So the first level is a vector. The first level is just the increment of the path. If you know, you can, this is simply the gamma t minus gamma 0. And of course, this is a vector because we're in d dimensions. The second element, the second level of the signature, this one, is a matrix, is a d by d matrix. And it represents the iterated integral of the I, so the ijth entry of this matrix correspond to the integral, the iterated integral of the ith component of the path gamma against the jth component of the path gamma. And so forth, and so on and so forth. The third level is going to be a d by d by d tensor. Fourth level is going to be d by d by d by d tensor, and so on. And this series of coefficients is apparently, okay, and so you might say, so what? But they have lots of properties, lots of interesting properties. The first one is sort of key for machine learning, which is this universal approximation property that I was trying to depict with the previous picture. So if you take a compact set of paths K, and you take a continuous function from this some compact set to R, then you can approximate arbitrarily well this continuous function for any path. You can approximate the evaluation of this function on this path as a simple linear combination of the terms of the signature. And crucially, the signature doesn't depend on the function. So if you change the function, you don't change the signature, you're just going to change the linear coefficients of the regression. So this is quite, some people, well, when we talk with signal processing people, for example, about these sort of things, of course, the first reaction is, we know how to extract features from a signal and then feed these features into our favorite model and do learning with it. And one way is, Fourier transform. The other way is wavelet transform, and all other different fancy spectral transforms. The problem is that all of these transform, I mean, they're amazing, but they don't have this property. They don't have, in other words, they are well designed to represent the signal, at least at the frequency level, with, the spectrogram, even frequency and time, but they have a good representation, they extract features that represent very well, or arbitrarily well, the signal, but not functions on the signals. And this is where really signatures and have this extra kick that make them interesting for machine learning. There are other properties that are worth mentioning, but I won't do that. I will not do that. But I will mention another property, which is also very nice, and this is built in, which is the following. So, in general, symmetries are not a good news for machine learning in general, because if you have an image You can rotate it of a dog, you can rotate it, still a dog, is the same dog. So how to teach to a model that is the same image. So how, in other words, how to build an invariance to such kind of symmetry, in this case, a rotation, is a problem if there is such a group of symmetries that underpins the data. Of course, one of the simplest, although expensive way of removing such partially removing such group of symmetries would be to augment the data. Augment the data set with rotated images and labeling them in the same way as the unrotated one, and teaching the model that should always be classified in the same way. That's okay with pre-images because they're, rotation in 3 dimensions is a 3-dimensional group, so it's a finite dimensional group. But when it comes to time series and to paths, continuous time paths, the news is bad because there is a group of symmetry which is really inherent to this kind of objects, which is called resampling or reparameterization. And here I've tried to give an example of such reparameterization. So on the left you have a path in 2 dimensions, 2-dimensional path. Here I've plotted the 2 coordinates on the same plot against time, but this is a 2-dimensional path. These are the coordinates parameterized by time. And then exactly the same path I have in the picture in the middle, the red one. I've plotted the same thing, but reparameterized with a quadratic acceleration. In other words, this is the same path, but instead of the x coordinate, instead of being cos 10t is cos 10t squared, and the y coordinate is sine 3t squared. Now on the right hand side I'm plotting
it's a phase portrait, right?
Sorry,
it's a phase portrait.
It's yeah, if you want, it's a parametric curve in 2 dimensions. Yes.
Yeah, when you plot the phase portrait, the time is not visible. You just look at what the trajectories look like. In any clock, the trajectories would be the same. That's what it is. Yes. Yes.
Yes, and exactly. So on the right hand side, when it's the x coordinate is plotted against the y coordinate, so to give the 2-dimensional curve, of course the 2 pictures collide and they're the same. But the problem is that any machine learning, not any, sorry, some of these 2 pictures on the left hand side are the same. They really are. And so in other words, there is a group of symmetries in path space that is called the time reparameterization. So these are increasing surjective continuous functions from a time interval to another. And so this is an infinite dimensional group where the operation is concatenation. Well, it's just composition of functions. And the signature, which is this psi, is automatically invariant to such things. So the signature of a path reparameterized by any reparameterization is equal to the original signature. And so the one nice property of the signature is that it removes this, it sort of acts as a filter that removes this repetition and this redundancy in the data. Just one of the properties. Right, so back to GANs and discrepancies. I don't know what I'm doing with time, probably very bad, but okay. So so if the space of functions f, so we have these nice properties of that the functions on path space are approximated arbitrarily well as linear function on the signature. So in other words, linear function on the signature, this is equivalent, form a dense class of approximators in the space of continuous functions on path space. And so in the supremum, defining the integral probability metric before, one can replace this class of functions f by linear function on the signature of the underlying path. And if you do that, after some manipulation, you can come up with this version of an integral probability metric, which equals the so there is no supremum anymore. This can be completely removed. And it just remains to compare this is a complicated operation to do. I will explain in a second why. The expected signature of the random variable x of the stochastic process x minus the expected signature of the stochastic process y squared. Now, these two things are infinite dimensional vector. They live in a space that is called the tensor algebra, and it has an inner product structure, and you don't need to know more about that. So this difference is obviously impossible to compute on a computer unless you truncate the signature and you use an approximation of it. Okay, but there is a good story, because there is a kernel underlying the whole situation. So it's very simple to see that, you know, just dot dot dot, but it's not very complicated to see that if you square this object, then you can express it as the sum of these three terms. Okay, so the expectation with respect to x of a k sig, which is, we call it the signature kernel of x with x, plus the same with y minus this cross term. And what is the signature kernel? Well, the signature kernel is between a path gamma and the path tau, is simply the inner product in this Hilbert space that I haven't told, this tensor algebra thing that has an inner product structure. And here it is, the inner product, which is the inner product of the signature of gamma with the signature of tau. So for now, the computation is still complicated, because in order to evaluate this expectation, I need to be able to evaluate an inner product between two infinite dimensional vectors, and it's still as impossible as it was to compute this original object. Okay, but of course, okay, so here we're entering the realm of kernel methods. Oh. Oops, I don't know what happened. I apologize for that. Share screen. It got automatically.
Oh,
this is real AI, actually. Sorry. Here you go. Yeah. Okay, so here we're entering the realm of kernel methods, and of course the question is it possible to have a kernel trick? Okay, so this is a kernel on path space. We have a feature map. This is a simple kernel using defined in terms of a feature map. This is universal, and so it has all the nice properties that one wants. But ultimately, for computations, do we have a kernel trick? Is there a way of evaluating this kernel on two paths without having to compute the signatures, or without having to compute the feature maps associated to the kernel? And the answer is yes. And this was some of my PhD work, which consisted in observing that it's not too complicated to see that the inner product between two signatures, so this signature kernel, solves a PD. And this PD is actually a very simple PD. It's a hyperbolic PD, linear. You see, it can be reformulated in terms of a wave equation. And it's, you know, you can, I did, you know, there are various ways of solving it numerically. There is no analytic solution, but there are effective way, even with finite difference, without going fancy with finite elements and so on, to evaluate very accurately the solution of this PD numerically. And so, in other words, this whole discussion allows to basically translate the complicated task of computing the inner product between two feature maps, so between two signatures, to the simpler task of solving it one-dimensional. Here, U is a function from 0t squared to r. So this is a one, you know, this is a, well, it's a, depending on whether you say d-dimensional for the input of an output PD. Usually people say for the input. So this is a two-dimensional PD if you want. That can be solved quite efficiently. So yeah, so and so just to close the hello, yes.
So if your PD linear or non-linear?
It's linear. It's linear in U.
It's linear in U, but the coefficient that you have, you know, depends on Cassie S derivative and gamma T derivatives, right? So you have a time variant coefficient.
Yeah.
I think, can you write down the analytical solution to this one by simply because it's time variance linear PD, right? I think it's possible to get an analytical solution.
Well, if you can you contact me? No, it's complicated. So you can actually do it.
No,
you can actually do it. You can actually do it. So if the paths are linear, so if the paths are straight lines, of course their derivatives are constant.
Yeah.
And so in that case, you will have a constant sort of factor there, and you can actually have an analytic solution in terms of Bessel functions.
Oh, okay.
Now, if you have time series, you can think of the time series as piecewise linear paths. And so if you set up your PDE grid by finite difference, you might think that on each grid you can actually solve this the PDE exactly. And so by simply chaining the solution throughout the grid, you get the answer. The problem is that even in the case, so this is an example of a Gursa PDE, which is a class of PDEs that were studied in the 60s that were resurrected in 2020 by this thing, but I mean, I'm happy about that. Anyways, the point is that even if this thing is constant, and if you don't have constant boundary conditions, but you have non-constant boundary conditions, then the solution will be analytic, but will be expressed in terms of an integral that you will have to compute numerically. And of course, this is only true at the first iteration of your computation. Throughout the grid, you will get non-constant boundary conditions, and so that basically break completely the hope for getting an analytic solution. But again, if you can see, we tried to find characteristics to solve ODEs instead of PDEs, but we haven't. This seems very naive and simple and innocent, but
yeah. So put it aside about how to solve this, whether it's analytically and numerically. But I think, as I understand it, the definition of the d-phi, this metric between these two path space, you have explored all the kind of phi, right? It's not one of it, all possible one, because you said it's selected from some dense set. You have to explore all possible. Does that mean that you have to solve like infinitely many this type of PDE?
No. The fact that instead of optimizing over any nonlinear function, you can optimize over linear function on the signature. It removes the optimization. It just throws it away. There is no optimization anymore to do here. It's just simply...
Look at the definition, the d-phi, right? But as your previous slides show, this phi has to be different. Then you take you screen or inf or something, right? It's not only one of it. So like say phi equals to square, like quadratic. So you need to take infinitely many of them, as I understand.
You mean psi?
Yeah, psi. Yeah, sorry, psi. Yeah.
Psi is unique. Psi is the signature.
Yeah, could you go back to the previous slides? I think you said that you need to go explore the whole space for the psi. Yeah, like this one. Psi key. Have a key of them, right? Or
so I mean.
Sorry.
This is just the kth coordinate. Yes, of psi.
Yeah, sorry. I got confused with previous definition. Anyway, sorry to interrupt.
No, it's fine. It's great. Thank you for the question. But this, I mean, if there are different. This is the maximum mean discrepancy. Okay, this is equivalent to taking the underlying space of function curly f to be the functions in the unit ball of an RKHS, and it turns out that the RKHS is actually the one associated to the signature kernel. But so there are different ways of seeing this thing, but the crucial property, and the Wasserstein distance, for example, is the supremum is taken over Lipschitz functions with a Lipschitz constant less than 1. So depending, and these are all different discrepancies. But for this one, you have the property that you can build a hypothesis test. I'm not going to discuss all of this stuff, but if you have two stochastic processes and you want to tell them apart, then you can use this MMD distance, signature MMD distance, to design an hypothesis test to tell them apart. And you can do the same thing for conditional distributions and blah, 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 blah. But anyway, that's sort of off topic here, but right. So putting things together, so this is just repetition. You have a generator that is given by this a neural SDE, and then a discriminator that is given by this signature MMD, the signature kernel MMD. And so of course you have an empirical estimator for this expectation, just you can make it biased or unbiased. Of course, unbiased is better, but slightly more to compute, but yeah, so this is sort of, you can put these two together and you can design very effective GANs for time series data. That is, the paper is coming out. I don't have the results to show you yet, but yes, that's, you can. No, okay, so now I don't know if I should stop. Probably it's a good idea if I stop rather than, well, I can maybe just show you a picture, because can I? Probably I can't. Can I do that? No. Yeah, so I mean, I thought I could, right, so let me see if I can, if I cannot even do that. I think that this is a good time to, so this is supposed to, you know, if I click on it, there should be a video appearing, but of course, doesn't happen. So but maybe I can actually unshare this, given that I'm almost done. I can actually unshare this and share the other one. If you give me 1 second, sorry.
No worries, take your time.
Yeah, sorry about this. So the problem is that one of the limitations is that these neural differential equations that so far I've explained, they are the state space of both the signal and the response, the input signal and the response is finite dimensional. So these things are paths. You know, the signal is a path with values in a finite dimensional space, and the solution is also a path with values in a finite dimensional space. But SPDEs, for example, are things that dynamical systems that look like this, right? I mean, can you see this video or not?
Yes, yes, we can see it.
Right. So the third part of the talk, I would say, would have been to explain how to sort of extend the ideas of neural SDEs or neural control differential equation more generally to treat situations of this kind. Okay, situation of this kind where, okay, the initial condition, this is the thing on the left-hand side, the forcing, so this is the driving signal, this has the same role as the Brownian motion, but if you freeze it at a specific time t, it's not anymore a vector, it's not anymore a d-dimensional vector, but it's a function. It's a function of space. And same thing for the response. This is a two-dimensional stochastic Navier-Stokes on the driven by a colored. This looks like pretty white noise. And on the right-hand side, you have the solution as well is a process with values in an infinite dimensional space of functions, in this case, of functions of R2. Okay, so you can think of this, these are two paths with values in L2. And so, you know, one way to deal with these sort of things would be, okay, let's discretize everything. Let's put a grid in. And so, okay, 64 by 64, for example. And so there you go. You have a control differential equation with paths with values in 64 by 64 dimensional space. Sure. But then, of course, this makes it's very complicated to train. It's very complicated to make it work. And then some people might say, now I want to evaluate my trained model on a 128 by 128 grid. Of course, you can't do that because the architecture is completely tied to the configuration of the original data. And so the goal is to extend what we did, but to to really make it a resolution invariant. In other words, to create a model that is able to process such signals without caring about the discretization of what one might choose to represent the signals. So once trained on a 64 by 64 grid, the goal is to make it evaluatable, if you want, on any other grid. And I think I can stop here because time is running and I don't think I have time to give any details about that. But of course we can talk about it if you. Thank you.
Thank you.
maybe I can reshare the screen just in case we need to point.
George, do you have any comments?
So what does it take to calculate how many signatures it takes to calculate? Do you calculate from such, like from a simulation like the one you said? You take 64 by 64 time series and then you calculate some signatures on each one of them? Sorry, I'm just not clear.
Yeah, it's actually a good question, and it's an open question, because the discrepancy that we could build on a finite dimensional stochastic process, but between two finite dimensional stochastic processes, relies on a kernel, the signature kernel, that is also geared up to take as input two finite dimensional paths. Now, the question is how we could do the same. We could build the discrepancy for, process which takes their values in functional spaces, space-time white noise, colored noise, things related to SPDEs, if you want, if we had a kernel for paths with values in infinite dimensional space. We don't yet. I mean, I don't. I'm working on it, but so for now, the way that we trained the neural SPDE model, which is what I haven't talked about, is not a la GAN. So we just trained it pathwise. So you give me a realization of white noise, a sample path of white noise, and I can evaluate the neural SPDE model on this path to produce another path, which is the solution of the neural SPDE, and then compare that path with the with the loss function to the true path, and train the model in this way. So path by path. We do not have for now a way of doing the same thing a la GAN, where we can start from a distribution like white noise, for example, and we are talking about space-time white noise, and then build this push-forward map by the neural SPD to get a distribution out, and then have a discrepancy that could be used to train this kind of models in the same way as I've explained for neural SDEs. We can't do that yet because we lack this. We lack, let's say, not only a signature kernel, but also a signature for infinite dimensional paths. I mean, if you want, you can define the signature for infinite dimensional paths, but the first level is already an infinite dimensional vector. So you're sort of screwed from level one, and yeah. So, but yeah, and this is an open question. I mean, it's a current research effort in our community. I mean, I don't know how many people are actually trying to do it, but it's definitely not solved yet.
I have a question, two questions, in fact. Okay, so the first one is, I was, the physicists use, bear in mind, a lot of physicists use, the Feynman path integral to represent, basically functional the probability density to represent the density for the stochastic process, right? So can you comment or anything on that in that regard? Because for me, it's also a possible way to design something metric to measure the differences between one stochastic process and another one using the functional Feynman path integral. That's of course very physicist thought. And another way, come to my mind is you get some, maybe PDE version of the Gassonov theorem, which is probably also the comparison between the probability merits in the functional sense. So I don't know whether you ever thought in that kind of direction, and whether it is helpful for in any sense. Just several.
No, it's there. These are good points. I mean, you also have the Chapman-Kolmogorov equations, the Fokker-Planck equation, which is an equation that governs the transition probability density of a diffusion process from going from T to T plus delta T, right? And you can write down PDEs, I mean, a parabolic PDE in terms that governs that transition probability. The Feynman-Kac is a PDE that governs a conditional expectation, right, of the process. And sure, I mean, these are ways of dealing with things, and I'm sure that there are many nice results that people have been using to train models using these sort of techniques. I was actually reading a paper recently, but my point about the density was simply that if you want to use, if you have random variables, usually the sort of first, I mean, the first reaction of people to do things with random variables is to look at their PDF, right? It's a probability density function. But if these random variables are on path space, that the only remark that I was saying is that you don't have, that notion doesn't exist. It is not possible to make sense of it. Then, of course, if you take the process at time t, and this is, this as a density, so is measured, I mean, it's differential with respect to the bag, then you have a path of density, and you can write down PDEs for such density. But in all generality, if you have a random variable on path space or stochastic process, you can't really talk about density unless there are quite heavy assumptions on things that make, you see, that's what's my
this is really called a function of probability density. So
okay,
have a look at it. Okay, another sure. Question is, another question. So I'm still a little bit curious. So what are your purpose of your neural networks? So because for my understanding, or you do a learning program, i.e., so you don't know what the underlying PDE, stochastic PDE really is, and you want to use your framework to learn what this PDE really is, stochastic PDE. Another one is a solver problem. That is, you know the exact form of the PDE, you want to develop a neural network to solve it. So I don't know how you describe your method. So in which category or
first? We're in the first. In this case, I mean, all I've talked about today is the first. So I mean, especially in the case of neural SPDs, the thing that we've done is that, okay, we have simulated data from an underlying SPD, then we hide the SPD, and we just have the data, and we want to retrieve the SPD. Okay. We want to reconstruct the SPD. Yes.
Yeah, thank you. That's all.
Thank you.
Do you have any more questions? Yeah. Okay, so thank you, Chris. Thank you for your presentation, and
thank you.
This is it. Yeah, this
sorry
is it.
To be late again. Sorry.
No worries. Okay, so this is for this week's Cron seminar, and everyone has a good weekend. See you.